Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you understand Newton's first law of motion. Now there's a couple different ways that Newton's first law of motion is stated, and here is one way that it's stated in textbooks a lot. Like, we're going to talk about this right here. So an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external force. Give or take a couple words, that's how I usually see Newton's first law of motion stated in a lot of physics texts. I like to state it like this. This is my version. It's a little bit, I think, a little bit more concise here, right? The velocity of an object will be constant until there is a net force that is not equal to zero. And what I mean by that is that it takes a non-zero net force to change an object's velocity. Or, when you think cause-effect, force is what causes velocity changes. Right? So what this means, this is my symbol here for observe. That's supposed to be like an eyeball. If you observe a change in velocity of some object, then the net force on it is definitely some number and not equal to zero. All right, so again, Newton's first law is about cause-effect. And it is force that causes changes in velocity. That's the gist of it. So I'm going to now pull up another program here, and oops. I think I'm going to. There we go. And we're going to talk about these changes. Okay, here we go. So we're going to look at a couple examples here of Newton's first law. And again, I want to tie it to free body diagrams, which I usually teach before I teach Newton's first law, or any of Newton's laws for that matter. And we're going to talk about it and tie it to what I call velocity graphs. Hopefully you've watched some of my videos. Oops, had the eraser on there. Hopefully you've watched some of my videos on how to use velocity graphs to describe the motion of an object. All right. So imagine this car right here. Imagine the driver gets in and then accelerates the car, gives it some gas. Right? A free body diagram of the car while the car is accelerating might look something like this. We have a gravitational force down. Right, we have surfaces in contact here and here. That's going to create what we call normal forces. And generally speaking, we just usually lump those together into one single force vector up, and we call it a normal force. Now, if the driver's giving it gas, right, then, and it's, well, I'm going to imagine it's a front-wheel drive car here. There's a frictional force created in this direction, to the right. Now, if you think about how vectors add graphically, or algebraically for that matter, right, these two force vectors are going to add to zero. And then this one is the net force acting on the car. Now I would point out that I left off small forces like the gravitational force of interaction between the car and the moon, and I'm going to just assume air drag is small because it is at low speeds, not an important force. So ignoring air drag, this would be a complete force vector, or a free body diagram. And the velocity graph during that time frame might look something like this over here. The velocity would probably increase pretty close to linearly. It's not important that it be perfectly linear for the discussion. Suffice to say that the velocity in this region is changing when we have a non-zero net force here. Right. Now, let me add this. A motion diagram for the car might look something like this. And I'm just going to use the dots to represent like the location of the car. And in this region might look something like this. Now, if the driver then, I don't want to say lets off the gas completely, but is just driving at constant speed now, right? Hits some sort of speed that he wants to occur and adjusts the gas pedal accordingly. The motion diagram for the car now, if I kind of continue on with that, it's kind of looking like this. Notice that what I'm trying to do here is I'm trying to make the delta x's about the same, constant, meaning this distance is about the same as this distance is about the same as this distance. The free body now is looking something like this. We still have a gravitational force. We still have a normal force. Now, when the car's moving reasonably fast, 50 or 60 miles per hour, there is a reasonable air drag. And I'll put like F sub A for air drag. And the motor has to continue to put torque on the axle, creating this frictional force. And what you'll notice now is that these two forces, you'll see, I'll say this, at least have the potential of adding to zero. And in fact, they do if the velocity of the car is constant. And we're in this region on the graph where the velocity is not changing. So this region on the graph corresponds to a free body like this, where there is a net force that's definitely not zero because of this. This region of the graph, where the velocity is constant, corresponds to a free body maybe like this. And you can see here, and in fact, it will identically add to zero if you added up all those force vectors. So again, a net force of zero, no change in velocity. A net force that's not zero, you'll definitely get a change in velocity. And let me talk about the other example here that I've that I wanted to chat about. All right, so case 2 here. All right, we've got this rocket in outer space here. And again, imagine this being a long way from the Earth, a long way from any planets where there's no gravitational forces really to consider. And the rocket, the driver turns the rocket engine on and creates, what we typically call a thrust. All right, and that's a force. And the force vector would go in this direction. So this is the force created by the, I'll just say the exiting exhaust fumes, right? There's basically a force interaction between the rocket exhaust and the rocket, forcing the exhaust to the left and the rocket to the right. And again, I'll probably use this example when I talk about Newton's third law. A velocity graph, right, in this region here might look something like this. We would expect the velocity to change. Now, whether or not it's perfectly linear, not really important for the discussion. I guess I would say that if the velocity, or if this thrust here were constant, the velocity probably would actually have some curvature to it because of the mass of the system is dropping, but that's not relevant for the discussion. Let's just imagine that the acceleration is, roughly constant, so it looks maybe something like this. So again, the important factor here as far as Newton's first law is concerned, we have a net force that is not zero, and we can see our velocity changing on the graph. And again, the motion diagram for the rocket might look something like this. Again, where the delta x's here would be getting larger, right? And the velocity is increasing. Now, eventually the rocket is maybe going to run out of fuel, or for whatever reason, the driver shuts the rocket engine off. Now a free body diagram basically looks like this. There's no external forces acting on this rocket, as long as we're a long way from planets and it's not colliding with any asteroids or aliens or who knows what else. So there's no force vectors to put in the picture. All right, and then again, I like to use the ... to kind of describe the motion of the, I should probably put them a little further apart here. So the ... which kind of visually represents the motion of the rocket, right? Our delta x's would be constant. Now I did this by hand, so they might be changing a little bit, but. And on the graph, our velocity is constant, so now we're looking like this on the graph. It's level again. Again, now Newton's first law. When we have a net force acting on the system, our velocity changes, and we're on this part of the graph. When there's no net force, or we can say the net force is zero, either case, no forces at all, or a case like the car here where there's several forces but they add to zero, then our velocity stays constant. So that's Newton's first law, kind of in a nutshell, and how it relates to graphs and free body diagrams. And I hope that this video helps you better understand Newton's first law of motion. Have a great day.